Hi, my name is Zachary Baker, and I will be demonstrating two types of Hall effect sensors today. Here are the variants of the Hall effect sensor. Today, I will be demonstrating a bipolar Hall sensor and a linear or analog Hall sensor. First up is the bipolar Hall sensor. Here is the internal design schematic of our bipolar Hall sensor. Upon introduction of a north pole, which causes a magnetic field into the page, the induced potential difference on the Hall plate causes the Smith trigger to reach its threshold and produce a high output. The out voltage in this case will be near the supply voltage. This will only change upon application of a south pole on the front face of the Hall sensor, which will cause the Smith trigger to reach its opposing input threshold by alternating the potential difference on the Hall plate, and will produce an output equal but opposite to the aforementioned result. The out voltage will then read low, which is nearly zero for a Hall sensor. This is the base schematic provided by the supplier for building the Hall sensor circuit I am about to demonstrate. Here's the Hall effect sensor circuit as per the schematic shown in the slides. I've added an LED to indicate when the Hall effect sensor is activated, and I've also marked the front side of the Hall effect sensor. We're going to use a permanent magnet. This side's north, this side's south, to activate the LED. So applying the north side will activate it, as you see there. And even when I remove the magnet, it stays activated as per bipolar Hall effect sensor functionality. Apply the south side, you see the LED deactivated. Now I will demonstrate a linear Hall sensor and use it to estimate the magnetic field of a homemade electromagnet. This measurement will be compared to Biot-Savart's summation approach for coils. Here is the internal design of the linear Hall effect sensor from Allegro Microsystems. The design is a bit more complicated, so I'll skip the details for the sake of time. However, it works very similar to the bipolar schematic shown previously. Here are the properties of my electromagnet, which will be used in Biot-Savart's summation approach. Please note that these are all approximations. This is the Biot-Savart formula when calculating the magnetic field intensity along the center line of my coil. Notice the 3 in front of the equation. This is not typical. I added it because I have 3 layers, and this is my estimation for the increase in field. Here are the results of applying the previous equation generated via the programming tool MATLAB. On the next slide, I will highlight how to interpret this graph. As you can see, the coils generate a magnetic field with the highest intensity being at the center. The regions of measure that I have indicated with the green color are the estimated areas that will form my data pool. This graph assumes equal spacing between windings with the equal number of windings on each layer. This of course is not exact, since I hand wrapped the coil. From the graph, you can see that approximately 30 to 100 Gauss is to be expected. Next, I will perform a demo showing how the linear Hall sensor takes measurements. Here's the linear Hall effect sensor demo. The circuit's set up the same as it was before. I added a resistor to the LED, so now it's sitting in a steady state. Here's my electromagnet supplied by typical battery. Pressing the button activates it. I have the permanent magnet placed inside. As you can see, upon activation, it becomes an electromagnet. I added the permanent magnet to give it strength so that you will actually see changes in the LED. The field's relatively weak. Taking the linear Hall effect sensor to the north side will do the opposite of what it did for the bipolar sensor. It will reduce the voltage output. And then coming around to the south side will increase the output and make the LED brighter, as you can see. Here are the voltage readings from the Arduino analog input. I have labeled the maximum and minima based on which pole was its cause. Notice the north reduces voltage output and the south amplifies it. This is exactly what we saw with the LED, just at a much lower voltage, since the permanent magnet was removed for the measurements. Now, using the results from my Arduino and a sensitivity formula provided by the supplier of the Hall sensor, I can approximate the magnetic field intensity. Comparing this to the expected 30 to 100 Gauss from the Biot-Savart summation, it is on the low end. This could be due to voltage reduction from the battery, energy loss via generated heat, which was noticeable after short runs, and any of my approximations. However, this does give a rough estimate for the intensity of a magnetic field and shows one of the many applications for a linear Hall sensor. In hindsight, I could have counted my coil windings and completed only one layer for a more exact approximation. Thank you for watching.